a proactive multicast solution which is based on mobility information and which is designed for offering seamless mobility support in cellular network environments. So let me, and it's a joint work between AUEB and the University of Essex. Let me start straight with defining the problem that we're trying to solve with the solution. So let's assume that this is a mobile user over here that you see, and that the user is currently connected to this cell. It could be a Wi-Fi cell, it could be a small cell, whatever cell it is. So when the mobile decides to move and to connect to next cell, there is a problem within ICN. Although ICN is mobile ready, still there is an issue with the fact that the mobile user needs to submit again its subscription, wait for it until it gets resolved, and then when it gets resolved, the mobile user is going to start getting the data. So this is not good news for delay-sensitive applications and for applications that have strict requirements with respect to quality of service. And the application for which we care more about in our research is video streaming. Well, an outline of the solution that I'm going to present you is this. I'm sorry for this mess. It wasn't supposed to be like that. So what you see over here is, again, basically the same idea. You see a car which is moving within a cellular environment comprised by various types of cells, small cells, picocells, femtocells, Wi-Fi hotspots. So the first characteristic point about our solution is that it is designed to take autonomous decisions with respect to proactive multicast in each and every different cell. Those decisions about proactively multicasting a content or not proactively multicasting a content are taken per object, and they are taken, of course, prior to mobile handovers. That's why this solution is a proactive solution. The other characteristic is that it takes advantage of mobility prediction in order to take such decisions. And we use a semi-Markov mobility prediction model, which predicts both next cell transitions and the duration between mobile transitions. So, as I said earlier, ICN is mobile ready. Apart from that, because of its pub-sub nature, it's by nature multicast. So we can actually take advantage of multicast to support mobility by multicasting the requested data into network areas. This is not a new idea. It's been proposed in the past several times. The bad thing about trying to handle large multicast populations with multicast, mobile populations with multicast, is that it's not a good idea when you do it blindly. Because then you're going to waste your resources. So for the last 4 or 5 years, there's been extensive research on proactive caching solutions, some of which we have worked on as well from our group, and which are based on mobility prediction. So you take proactive caching decisions based on information about where the mobiles will move to next. So being influenced by those solutions, we came up with our current model, which is a proactive multicast model, which decides based on mobility prediction about where to start, which network areas to start multicasting the information. And as done in the case of proactive caching, where you've got a restricted resource, and that resource is the backhaul, again here we identify as a restricted resource which we have to utilize in a clever way, the backhaul connection of each and every small cell that we run our solution. So, our model. First of all, I'm going to talk about the general idea of the semi-Markov prediction model. Well, it uses a history of mobile transitions in one network composed by multiple cells, what it actually needs as an input is a list of successive cells visited by mobile and the residence times in each and every of these cells. And the model can be trained both offline as well as online. The second thing is that this model assumes an arbitrary distribution of residence times, which is convenient because it moves away from a common assumption, in other words, which is that residence time is exponentially distributed. And this is, it's not complicated. So if this is a probability of moving from cell I to cell L. How do you compute that? Well, this is the number of transitions from the current cell I to the next cell based on a history. And this is the total number of transitions. So you get this probability over here. Now, this one looks similar, pi looks similar to psi, which is again the same thing, only this time you take into account the time interval t within which a mobile transition takes place between cell I and cell L. And based on pi and psi, we define this kernel over here, phi, which is the product of these two. So by using phi, we can actually predict which is going to be the next cell, most probably to be visited by a mobile, which comes from cell I and it's going to move to another cell. And for the rest of the model, we're going to use this kernel as our transition probability for mobiles which are currently at one cell and may move to another cell L and which request for an object S. Talking about how decisions are taken autonomously in each and every cell, well, the first thing is that we use the summation, the sum of all the probabilities by mobiles which are currently connected to cell I and want to move to cell L and which request for the same set of objects S. So by using Q over here, as well as a cost in case the cell moves to, in case the mobile moves to the cell that we have predicted is going to move, and a cost in case our prediction was wrong, we come up with a decision model, which is the one that you see over here. The decision is positive, which means that we decide to proactively multicast an object S in cell L if the expected cost gain, in case a mobile moves to this cell, is higher than a congestion price. You see the congestion price over here. This congestion price refers to the backhaul, which is the congested resource, and it's dynamic. It adapts to the current demand conditions, and which increases with demand, and when demand drops, it decreases as well. So the idea is that if the expected cost gain is higher than the current price of the backhaul, which you have to use in order to proactively multicast the objects, then you decide to proceed with multicasting S before the mobiles move to this cell. Otherwise, you don't. Now, apart from the basic model, we have also tried an extension to the model. We get rid of the pricing, and we replace that with adopting a replacement model, which tries to always keep a list of the objects with the highest expected gains in the list of the proactively multicast objects. Obviously, we do this in order to try to have to capture actually temporal locality better than with the pricing model, but it comes with a cost. And what is this cost? While with the basic model, the computational cost is fixed. In this case, it depends on the number of n previous decisions that you have already made with your model. So there is a price to pay for this extension. And based on this, we've done some preliminary performance evaluation of our model. What we actually did is that we used a realistic car traffic mobility trace from the city of Cologne. We also combined that with a realistic cell distribution, again for the city of Cologne. We assumed cells of this range of about of the radius of about 500 meters, and a backhaul connection of about 20 megabps. For practical reasons, we had to break the simulation area into 6 samples of this space, 2.5 kilometers by 2.5 kilometers. In order to proceed with our simulations, we assumed a video file request which come from a synthetic from a set of synthetic traces produced with the GlobeGraph tool. We decided to use this setup for the zip-fin distribution, and we actually combined this trace, the file trace, with the trace of mobility and the trace of the cells, and came up with this. What this graph shows is the gain from our solution against an almost 21-hour period in the city of Cologne. We show the performance of the basic model, the performance of the extended model with replacements, against 2 benchmarks. Max pop over here, which is the yellow line, shows the gains that you have if you only consider long-term popularity of the objects, which are being proactively multicast. Naive means that you actually take decisions blindly. If there is room in the backhaul, you are one of the possibly next cells in a transition, then you grab the resource if you can do it. Another thing before explaining the result is that we assumed that in case of a hit, you got a 90% gain, which means that there is a 10% of cost which you cannot avoid. Perhaps, well, this is because we assume that 10% is the cost of connecting in the MAC layer, which you cannot actually skip anyways. And let me now proceed with explaining what this graph shows. So first of all, you see that the curves have fluctuation. This is because the demand over this period of time changes. When traffic increases, demand also increases. And this is why actually in the yellow curve, you see that there is an increase over here over this period of time and an increase over this period of time, because this is the point of time where traffic increases, so demand increases. And this is why taking decisions based on popularity can actually increase its performance. Nevertheless, this curve over here is way below our model and even the naive model. And this is because judging only on content popularity, you cannot actually capture temporal locality of requests, which is something that you do even with blindly allocating the resources. Another thing is that you can actually see that when the performance of popularity increases, the performance of the rest of the curves tends to, like over here or over here, tends to converge for a while. But when the performance of max popularity tends to decrease, which means that demand decreases, the performance of the rest of our solution and of the naive solution tends to increase. Now, the reason why our solution is better than a naive allocation of resources is obvious. It's because we take into account fresh information about where the mobiles are going to move next, and we also take into account the objects which they request. So we make a better prediction. And the reason why our basic model is actually not as good as the one with the replacements, the extended model, is again because of the same thing, because when you adopt replacements, you actually achieve to have always in the list of proactively multicast objects the objects which are expected to have the highest gain. But here, where all the algorithms tend to converge, actually, at this point over here, we can see that the difference between the basic model and the extended model is, well, it is about 15%, which is not that big compared to the fact, well, relatively to the fact that the basic model has a very low computational cost, which is good news for the basic model and for the simplicity of our solution. And that was the results of our preliminary evaluation. Our conclusions are basically that we have shown with these results that we can reduce actually the transfer cost to a new cell based on mobility prediction. In PubSum environments, the cost refers to reducing delay, the delay that you need in order to resubmit your requests, have them resolved, and then wait until data starts to flow to the mobile user. In a different context, with regular TCP/IP, the cost reduction can actually refer to the fact that you avoid the time needed in order to reestablish a client-server connection. And our results have shown that our model can actually adapt well to temporal locality, and this is again because we take advantage of fresh information about user demand and fresh information about the mobility of each and every user which submits requests. And, well, this final comment over here is that apart from temporal locality, we see that our model can actually take better decisions than a very naive model that actually takes advantage only of content popularity in the long term. And that was a short presentation. That's the end of it. I'm ready to accept your questions. I see no questions.
So can you please go back to the graph? So yeah, I know like why it's increasing with the passage of time, like is it learning more and more?
This is actually a good question. Well, first of all, it increases because demand levels increase, and secondly, because as you said, the system gets trained. In the first, well, regarding the basic model, the pricing, the condition pricing model that we use converges better to adapt to current demand conditions. And the general answer to your question is that it gets better trained throughout time, and that's why it converges after a while.
So like in your traffic model, like with the passage of time, the gain, like demand was increasing.
The demand was increasing, but then was decreasing again, which is something that you can see easier when you take a look at the yellow line.
That's what my question is, because when the yellow is going down, then when demand is decreasing, so why in the red curve is going down as such?
Well, when demand is going down, such as, for instance, in this region over here, the model tends to have a better performance because it adapts better to temporal locality.
The gain would be higher, okay.
It's because when demand gets low, as we've seen in past work that we've done, this kind of decisions based on pricing tend to capture niche demands by users, not generally popular demand. And this is why you actually see that being based only on general popularity actually doesn't go that well.
Why are there the dips at all? What's causing? I mean, they've all got this sort of apparently cyclic kind of behavior.
Well, this is throughout a period of almost 24 hours, it's 21 hours.
Real traffic demand.
It's traffic demand. So if it's late at night, it's going to go low. If it's early in the morning, it's going to be low again.
One last thing, like I didn't see probably the network model of we were seeing like what are the assumptions here, what are the assumptions about the network model as such. Like these decisions have been taken at the, I assume that this decision are taken at the UEs rather than at the network level.
These decisions are taken by each and every different cell. So there is an instance of the solution running in each and every cell. which gathers information about the mobiles which request for a specific object and which are in a neighboring cell nearby.
So who monitors the data?
So the cells, let's suppose that you've got one cell over here and you've got a mobile user which is connected to the cell. And you've got a list of something like 5 different cells where the mobile can move to next. So you predict, based on the semi-Markov mobility prediction model, what are the probabilities. You feed these probabilities to the decision model of the next of each of these 5 cells, and every one of these 5 cells decides based on this. So any of the neighbors is going to assume a different queue over here, and perhaps even a different cost gain. So decisions are autonomous. And another important thing is that the local congestion price of each of the neighboring cells is not the same. It's different for each and every cell. It depends on its local demand.
Right, but if that decision is made by the future cells,
Mm-hmm.
but the one where you are now is the one that is going to multicast the data to the future cells, or
No, it's the future cell which is going to start multicasting the data before the mobile makes a move to this cell. So once the mobile moves to the next cell, perhaps this is better shown with the first graph that I showed here. So when the mobile moves over here, once it gets here and gets connected to the cell, it starts to get the data straight away without having to reestablish a connection to the server or submit its subscriptions again.
That is already the case currently in the server system design, because they use the tunneling mechanism from the old cell to the
Yeah, we're not using tunneling here. So this, within an ICN context, this possibly future cell could actually submit in advance before the mobile makes a move over here, can submit the subscriptions and start to get the data. As I said earlier, ICN is already multicast in nature. It's intrinsically multicast, so you can do that in advance. Outside the context of ICN and outside the network level, you can do that even with TCP/IP. Only in this case, our solution is more of an application level solution than a network level solution.
I think one of the citations, we've got a paper that shows anchorless mobility, and I think we're hoping to get a transactional network paper soon on the anchorless mobility solution. And the benefits it gives, of course, it's not hard to see what benefits you can get with anchorless mobility.
One last question, like, what are your thoughts, like, if we're gonna do the same decision at the leads, for example, like,
you can actually do that. You can actually do that with, I suppose by UE you mean the mobile itself.
Yeah,
You can do that, only in this case you need to let the mobile to decide, which means that after taking the decisions, the mobile needs to send a message to the possibly next cells and let them decide. If you don't like this, you can even do that centrally. If you combine this idea with within a heterogeneous network environment composed by a large cell and smaller cells, you can let the operator of the big cell to decide. Then perhaps you can even have a better prediction because the mobiles might have already told you when they're going to move and where they're going to move.
Thank you.
Any other questions?
one last question. So you here assume that you know the exact data or the exact pieces of data that
Yes, since this is an ICN solution, and since we're working on the Pursuit project, you actually need to submit a specific request for a specific object. So you have to declare that I'm watching this video right now. Yeah, and let me remind you that this model also takes into account prediction with respect to the residence time. So you do not really need to multicast everything. You only need to multicast everything starting from a point in time in the future. Thank you as well.
Yeah, so the next speaker is Ben Yuan. He's a PhD student with the 5G IC group